right? It's 12:50. Oh, is it? Okay. Can you hear me now? Yeah. Um, yeah, so today we have three very exciting talks. The first speaker will be Dave Jewitt from University of California in Los Angeles, and he'll be talking about the Trojan color conundrum. Next will be Bonnie Buratti, who's from the NASA's Jet Propulsion Lab, and she'll be talking about continued volatile transportation on Triton. And third, we'll have Teddy Kareta from University of Arizona, who'll be talking about the physical characterization of 3200 Phaethon, which is the target of the Destiny Plus mission. So we'll have the three speakers speak for about 10 minutes each, after which we'll take Q&A from those present here and those present online. So, Dave.
I'll just double click.
Yeah.
Okay. So where are people looking? Oh, really? Okay, great. Great. So the Trojan color conundrum. So the Trojans are these bodies which move in the orbits of planets, but never meet the planets because they're librating around what are called the Lagrangian points. So they're 60 degrees ahead of their planet and 60 degrees behind their planet. The first one was discovered in 1901, so they're about 100 years old. And now we know of many thousands at Jupiter, and we even have some at Neptune. But we don't know much about them. And so there are several big questions about the Trojans. The big ones are how were they acquired by their planets? So they're captured. How were they captured? When were they captured? And where were they captured from? Would be the three leading questions that jump into my mind, at least. And a lot of people have those same questions. Now, there are many different possible answers. There are models for everything in planetary science, right? And the question is, how can we discriminate amongst models, make new models? So extremes for the Trojans. One extreme would be that these are bodies that were originally present in the protoplanetary disk and were orbiting near the planets that ultimately captured them. And there are various schemes by which that might happen. One scheme, for example, involves the rapid growth in mass of a giant planet. We think that the mass shot up from a small value to a big value relatively quickly. And when that happens, the gravity of the planet becomes much more important and can stabilize the orbits of bodies nearby. So it could have stabilized asteroids that were previously moving in independent orbits into these Lagrangian clouds, the Trojan clouds. That's one possibility. And actually, that's a very good way to obtain Trojans because the probability of capturing a body depends very much on the encounter velocity between the Trojan and the planet. So basically the analogy is, if you throw me a ball, I can catch it. If you shoot a bullet at me, I'm not going to catch it. It's basically like that. So coming in slowly from a nearby orbit is a good thing. But for whatever reason, the planetary science community has settled on another extreme model in the opposite direction, in which the Trojans are captured from a distant source, specifically from the Kuiper Belt. And so the Kuiper Belt objects will be coming in at high speed, and the probability of capture is very, very small. It's like 1 in a million, according to these n-body models that people run. 1 in a million bodies could be captured in a Lagrangian cloud, a Trojan cloud. So we don't know what's going on. But it would be nice to know what's going on, to understand the origin of this population. So it seemed to me that a simple test, the dumbest test you could think of really is to look at the colors of the Trojans and compare the colors, the color distribution, with the color distribution of the populations in the Kuiper Belt from which capture is suspected. So you would expect that you bring objects from the Kuiper Belt, you put them in the Trojan clouds, they should look basically the same in color. But we've known actually since the very first Kuiper Belt color measurements in the middle 1990s that that's not the case. So we know that in the Kuiper Belt we see this very red material, ultra-red material, which we think is organic in nature. We think is cosmic ray irradiated organic material. We don't know that, but we think that. It's present in the Kuiper Belt in some considerable abundance, but it is not present, it's not seen in the Jupiter Trojans. So we already know that the Jupiter Trojans don't look like the Kuiper Belt object populations from which they are supposed to have been captured. And the resolution of that, in my mind, was, well, you know, you bring something in from the Kuiper Belt, it's at 40 Kelvin or 50 Kelvin out there, it's really cold. You bring it into Jupiter's orbit, where the temperature is probably 120 Kelvin. So it's much warmer, it's 3 times warmer. And so you enable various processes. Chemical processes can occur. You can crystallize amorphous water ice. Stuff can happen that could modify the surfaces of the bodies brought from Kuiper Belt into the Jupiter Trojans. And so that was it. Until recently, that was it. But now we have the Neptune Trojans, so recently discovered population of Neptune Trojans. And they offer a different test because at Neptune's orbit, this process of thermal modification won't work because Neptune is at 30 AUs from the sun. It's basically as far away from the sun as the Kuiper Belt. Temperature change in going from Kuiper Belt to the Neptune Trojans is negligible. So these chemical and activation processes won't happen in the Neptune Trojans. So you wouldn't expect to see a difference in the Neptune Trojans. So the question is, do we? So the answer is sort of summarized in this plot, and I'll show different versions of this plot. But basically, this is a plot of 2 different colors measured in the optical. So numbers to the right on this diagram mean redder, and numbers up on this diagram mean redder. So the reddest things in this diagram are up at the top right. And the yellow dot is the color of the sun. So everything in the diagram is redder than the sun, but the Kuiper Belt objects shown in red are all very red compared to the Trojans of both Jupiter and Neptune. So we've got measurements of 16 Neptune Trojans that show that the color distribution of the Neptune Trojans is very much like the color distribution of the Jupiter Trojans, but very different from any of the Kuiper Belt populations from which capture might have occurred. Okay, so that's the basic result, and I'll say that about 3 times in 3 different ways. So here's another slide that shows that. This is a histogram of the colors. The Trojan colors appear at the top, so the Neptune Trojans are at the top, then the Jupiter Trojans, and then there are different kinds of Kuiper Belt object. And you can see by eye that the 2 top histograms are different from all the other histograms because there are not many bodies on the far right. Look at that vertical dotted line, that's where the ultra-red matter begins. There are not many ultra-red objects in the Trojans, there are many in the Kuiper Belt populations. So the fact is we have 1 Trojan of Neptune, which is ultra-red out of 16, whereas in the Kuiper Belt populations, it's 1 in 3, which are ultra-red. So that's the observational difference. And so your eye can see that difference, but people like statistical tests for some reason, so you apply obscure statistical tests, and they just confirm what you see by eye, which is ideal, of course. So we have this difference between the populations. I'll skip over that to save time. So the conundrum is that the Trojans of both planets are different in their color distribution from the populations from which the models indicate they're captured. They don't look the same. And yet, there is no known process by which the colors could be modified, both at Jupiter, where it's hot, and at Neptune, where it's cold. That's the conundrum. So nature is giving us a little bit of a punch in the eye right there by presenting us with this problem. So how might this resolve? So I can think of at least 3 ways. First of all, it could be that we add more data and this difference will go away. Now the statistics shows that that's unlikely. It could be that the next 10 objects we observe turn out to be ultra-red, but statistically that's unlikely. Okay, it's less than a % chance, 0.4% chance that that will happen. But keep your mind open, it's possible. Or we might be able to identify a process that can resurface the Neptune Trojans. So in going from the Kuiper Belt, a few AUs into the Trojans, maybe there's something that happens that we haven't clarified. One idea that comes to mind is a non-thermal process. So it doesn't depend on the temperature of the body. Maybe it's collisions. And it's been pointed out that the Trojans can be hit by Plutinos, which are things like Pluto with resonant elliptical orbits. The trouble there is that the rate of impact is far too small to have any observable signature, so we wouldn't expect to see color changes as a result of this impact. And in addition, the idea that impact is going to convert a red object into a blue object is rather magical. There's no actual reason, physical reason why that would happen. We just conjecture that that might happen without evidence. And then the last one is probably the most interesting to me. It's the idea that, well, maybe the Trojans are not captured Kuiper Belt objects. Maybe they come from somewhere else. So I think that as we get more data, we'll be able to discriminate between these three possibilities. And the key thing as an observer is that this is a simple observational test of the hypothesis that the Trojans are captured Kuiper Belt objects, and it's a test which the model fails. Okay, questions?
We let Bonnie speak. Questions will come after.
You don't do the questions straight away?
No.
Okay, then no questions. I'll hit this reset button.
Yeah.
Done.
So I'm here to talk about seasons in the outer solar system. And I'm going to talk about an object that we really haven't been thinking about for a while, just to kind of refresh everyone's memory. There was a close flyby of Triton. This is the largest moon of Neptune. And it's a good follow-on to Dave because it's probably almost certainly a captured Kuiper Belt object. So this is kind of the first time we ever looked at a Kuiper Belt object. In fact, during the Pluto encounter, we thought that Pluto was going to look like Triton. Well, it doesn't. It's its own unique world. So just a few facts here. So this is an image from 1989 from the Voyager spacecraft. So it's 30 astronomical units from the sun. It's big. You know, it's one of the largest moons. It has a thin atmosphere, and we expect to see the seasonal transport of frost from the south to the north and back and forth over a 165-year season. It has a high obliquity, it's tilted, and it has an atmosphere, so we're going to have seasons. Let's see. Okay, so what we see here, see if I can get I did want to, I guess there's no pointer on here. So what we see there at the south, the southern pole of Triton is a polar cap, and it is sublimating during the Voyager encounter because the subsolar point, that is where the sun is overhead, is near the center of that cap. So here's a really nice map that Paul Schenk put together. And you can see there's the polar cap. There were 3 active plumes and a bunch of plume deposits discovered. And it looks like there's frost being deposited at the edge of the polar cap. Now here's what the subsolar point looks like. So that's northern summer in 1908. 1952, the equinox. This was a Voyager encounter. The subsolar point is there, 1989. Southern summer, 2000. Now the subsolar point is starting to go north, 2017. That's the year of the data I'm going to talk about, this new data that we have. Now we're going north. The equinox again in 2046 and 2091. So you really have to observe Triton for a long time to see these seasons. The spacecraft images give us an instant in time, this really clear picture. But to get the dynamical situation going on, you really have to look at Triton as a pinpoint of light from the ground. So we were really interested in this whole topic. We were observing Triton from the ground, thought we saw the frost patterns changing. And then what we did, James Bauer, Gerbis Bauer led this team, a Hubble Space Telescope map showing brightening towards the equator about 16 years about 16 years after the Voyager encounter. So these are areas, on the bottom there I have that map that Paul Schenck put together. And here are the two areas. This is a Hubble Space Telescope map. Of course, it's much lower resolution. Here are two areas that are brighter than they were in the Voyager observations. Okay, so now we're back to looking at Triton as a pinpoint of light. And, astronomers have shown you can get a lot of information out of pinpoint of light. So the other thing that's really cool about this project is it's all done by students. I actually did not take a single one of the observations I'm going to talk about. The students did all the observations from the Table Mountain Observatory. It's a facility that is owned by JPL. It's up in Wrightwood, up in the mountains nearby. And there's a 24-inch telescope up there that we've used as a workhorse. And I should also say that this program was supported by the NASA Planetary Astronomy program. It's got a 24-inch telescope that we've used as a workhorse to look for volatile transport on Pluto and Triton. Just by looking at light curves of these objects, we have been able to scope out volatile transport. And then, of course, it's been confirmed by Hubble or by spacecraft observations. So here's our data, and this is a little technical, so let me explain. Triton is a pinpoint of light, so we just see the integral brightness as a function of time. Okay, so if we look at Triton rotate underneath us, underneath the observer, we get what is known as a light curve. This is brightness with respect to time. It's a single point, but it gives a rough map of what the brightness is as a function of sub-observer geographical longitude. Okay, so where you see those little dots go up, each one of those dots is the brightness of Triton as a function of time in its orbit. Its orbit is about 6.4 days around Neptune. So those dots there on the bottom, and it's about a 10% change from top to bottom, give us the brightness of that pinpoint of light as it rotates underneath us. Okay, so this is what we found. Hubble in 2005 found brightenings. The sub-map there is it's Paul Schenck's Voyager map. Okay, so Hubble observing in 2005 found these two brightening areas. Okay, now if you look at the areas from this pinpoint of light, the light curve, the brightest points are there. So that's consistent with what Hubble saw. But then there's this new area here that looks like it's an area where frost is being deposited in the Voyager images. So we think that that is just continuing. And here is the other high point in our data is also where the Hubble data shows a brightening. So we think, and this needs to be confirmed, we need to watch this, but we are seeing hints as the sun moves towards the equator and then towards the north over this long period of 165 years, we are seeing frost being transported from the polar cap in the south up to the equator, and eventually it may be transported towards the northern pole. We can't even see the northern pole. It's not illuminated at this point. Voyager didn't see it, and we don't see it from the ground. So what is happening in the north, we really can't see, and in our lifetime, at least my lifetime, I never will. But perhaps there is a northern polar cap. There might be a small one up there that's going to grow. We just don't know. Future generations of astronomers will have to tell us that. So Voyager images show, this is my conclusion slide, a large sublimating polar cap on Triton as the overhead sun point moves south. Now it's begun to move north. Hubble detected frost moving towards the equator. And these telescope observations that we are taking suggest that this process not only is happening, but it's continuing. And spacecraft, this is a lesson, that spacecraft observations are spectacular. I mean, just look at what New Horizons did to a similar body, but they're an instant in time. You have to get these ground-based observations to kind of get the temporal progressions that happen over decades, and in this case, hundreds, centuries of years. Thank you.
Okay, so while that's loading up, I'm Teddy Kareta. I'm a second-year graduate student at the University of Arizona, and I would be remiss if I didn't note that this paper actually got accepted about 45 minutes ago, so it's a little bit more fresh. So I'm going to be talking about this really interesting object called Phaethon. The number is 3200. I'm not going to say it again. And we have this really nice artistic drawing of it in the background of these talks, and that's available if you're interested. So the reason we care about small bodies in general, and this is big picture, is that they should record something about when and where they formed. And for most small bodies, we think that they formed in the earliest era of the solar system. It's not as simple as just looking at them, figuring out what's in them, and then saying that was there. You need to figure out how they've changed since. So one thing that's really useful in this sort of area is to study bodies that are actively changing now, and try to use that as some sort of inference to figure out how they were in the past, and maybe how many small bodies of the millions in the solar system, how they've changed. So Phaethon is really good for this kind of thing. So until the 1980s, all known meteor showers, especially the really bright ones, had been thought to be made only by comets. So as comets move around in their orbit, they leave behind a debris trail. So the dust that they produce that you can see with your naked eye, it gets left in their orbit, and you see that as it contacts the Earth. However, the Geminid meteor shower, until 1983, no one knew which comet it came from. So in 1983, Phaethon is discovered, the first asteroid to be discovered from space, and it's in an orbit that is very similar to the Geminids. So it's thought to be the parent body of the Geminid meteor shower. It's really weird for a lot of other reasons too. So Phaethon, like the Geminids, is in this very eccentric inclined orbit. So the orbit is it gets very close to the sun. Naturally, at the closest point to the sun, the temperature on the surface of Phaethon can reach 1,500 degrees Fahrenheit, which is actually high enough for certain metals to start melting, namely aluminum. So you'd think that would actually have a lot of different processes that are acting on it, and it's part of the reason that it's changing today. Also, as you can see from the illustration itself, Phaethon is actually blue in color. So in sunlight, it reflects blue light much better than it reflects red light. So to summarize the kind of basic pitch for why I think you should care about this object, it's a weird blue asteroid that created the Geminids and gets so hot that metals on the surface turn to goo. So the big picture questions that we were interested in answering before we actually collected any data were, one, fundamentally, what is Phaethon? Is it a dormant comet? Is it an object that made the Geminid meteor shower in the past in a normal way, leaving behind a debris trail, and is now just run out of gas and dust to shoot off? Or is it something different? Comets are, generally speaking, red in color, and Phaethon is blue. Maybe Phaethon is just some sort of strange asteroid that wandered too close to the sun, and we are seeing, the ultimate edge case. Furthermore, the Japanese Space Agency, JAXA, is going to Phaethon. So in 2025, it's going to have a high-speed flyby of the object, and we're going to have more information than ever to actually know what this object is like, what it was like in the past, and what that tells us about small bodies in general. So we did this technique called reflectance spectroscopy. So we're looking to see how it reflects light, like how they were talking about reflectance colors. Broadly speaking, we did spectroscopy, so it's even smaller bins, so we can tell how reflective it was over a very long range of wavelengths of colors, very precisely. So we did it in the visible and in the near-infrared light. In the near-infrared, we did it last December. There's a picture of us on this slide. It's the only good picture of me ever taken at altitude. And this was during Phaethon's incredibly close approach to the Earth. It got close enough that you could see it even with just a telescope in your backyard. And we also got visible observations using a smaller telescope, not the NASA Infrared Telescope Facility, which I should have mentioned, using a telescope in Arizona about 10 years earlier, which one of our co-authors had already taken. So I think we have two results that I'd really like to highlight. The first one is that we find a new albedo for Phaethon, so it's a new amount of reflectivity. So Phaethon is darker than we had previously observed. So we observed that it has an albedo of about 8%, which is slightly brighter than charcoal. Charcoal is like 4 to 6%. And our second result, and I'm going to explain both of these, is that it is essentially uniform across its surface. So we watched it as it rotated, and we measured to see how it reflected light at every given point as the object rotated in space. And we didn't see really any changes. There are subtle features, but the big story is that it's essentially the same whenever you look at it. So why would you care about the albedo? So primarily, Phaethon has been suggested to be, to tie together all these different disparate pieces of information, a fragment of this other blue asteroid, the much larger Pallas. Pallas is out in the main belt of asteroids. However, Pallas's albedo, is about twice what we found for Phaethon's albedo. Previously, people had suggested that these two are related because they had these very similar, responses to light. They had very similar reflectance spectra. But we think that, if the albedo has changed so much, it's been decreased by half, and the spectra hasn't changed, I think it makes more sense to say that these objects coincidentally look similar because their albedos are so different. This is really kind of the way that people talk about Phaethon nowadays. This has become the paradigm. I have a screenshot of the Geminids Wikipedia article at the bottom, and you can see that it lists that Phaethon is probably Palladian in origin. All in all, we don't think this is done, but there's a lot of really important lab work in particular that could help, but we think that this is definitely a move away from Pallas as the origin. The second result is that the surface is homogeneous, as I mentioned, so it doesn't change very much as it rotates. Previous work on the subject had suggested huge variation, that anytime someone pointed a telescope at Phaethon, if you're looking at the right wavelengths, and these are typically short wavelengths, blue to your eye, it would look really different. So some people would say it was very reflective, some people would say it was less, neutral, the entire range. And if we watched it rotate the entire time and saw no change, one, that suggests that the whole surface looks similar, and previously people had suggested that might be the case. Every time it gets close to the sun and it gets newly scorched, at blowtorch-like temperatures, it's basically that's happening the same on every side, and given enough time, it should even out. But maybe all that variation reported by previous observers is right. Our observations didn't quite see the North Pole of Phaethon. So if that variation is real, maybe the North Pole of Phaethon is actually quite different. And luckily, Destiny Plus can just check this. They will see it. They will take images. We'll know. And there's a couple other lines of evidence that suggest that you might think that maybe Phaethon's North Pole kind of stands out. So I think there's some important future work that can hopefully at least help to nail some of this stuff down, because I know it might seem sort of just endlessly complicated. There are two candidate fragments of Phaethon, so large kilometer-ish sized bodies that fell off or were knocked off of Phaethon at some point in the past. 2005 ED, which is blue in color, which I drew with a blue circle, and then there's 1999 YC, which is red in color, which I do with the red circle. I think that the way forward is probably to actually try to integrate studies of Phaethon, these two little candidate fragment bodies, one of which we're already working on, and people who study the history of the Geminid meteor shower in general, trying to figure out when it was made, when it was produced. The Geminids are actually very young. The Geminids that are impacting the Earth today are no more than 1,000 years old. Putting all these information together, I think that's probably the way forward, though. We'll have to see. So in summary, I have an exactly tweet-length summary, 240 characters. But we investigated the strange near-Earth object, 3200 Phaethon, the parent body of the Geminid meteor shower, and found it to be darker and more homogeneous than we expected. These results are really a big asset to the people who are planning the Destiny Plus mission to, for instance, prioritize viewing the North Pole. And they also complicate our understanding of the object, because if it's not from Pallas, it's not like we have a better idea. We just know we don't think it's there. If any of you are interested in the image on the background slide, it's on my website, which is right there. So thanks.
Thanks to the speakers, and we'll take any questions.
Hi, so Luca Maltagnati from Nature Astronomy, and actually I have 3 questions, one each. Can I do them all? So for David, from what you see on the color distribution, you showed that the Trojans are not similar to the population where they could come from, but it seems that they're not similar to any of the population that I saw that you plotted.
They're similar to each other.
Yeah, only to each other. So the question is there any other kind of category of objects in the solar system, like in the asteroid belt or whatever, that have a similar distribution? And if so, could it be possibly dynamically that it could come from there?
So the asteroids in the main belt are, on the average, less red than the Trojans. So they're statistically not the same. And the stuff in the Kuiper belt is redder than the Trojans. So the answer is no.
So they're just...
There are some models, many models of everything, but there are some models in which Jupiter Trojans are or were main belt asteroids scattered out and captured by Jupiter. Neptune is so far away, forget it, never going to happen. So I think they're not main belt asteroids, and this model of capture from Kuiper belt is not supported either.
So the question where they come from is quite hot.
Well, it looks like they come from, I mean, it's consistent with the Trojans coming from regions that were near to each other in the beginning and then maybe separated out to where Jupiter is at 5 AU and Neptune at 30 AU. And actually, this morning there was a talk, the first talk in this session 200 had such a model in which Jupiter and Neptune and the other planets formed in a relatively narrow distant zone, maybe 15 AU, something like that, and then migrate inward to the sun, roughly to their present locations. And so they span out, they separate, but they drag with them Trojan bodies. So that, you know, at least on a conjectural level, that looks like it fits the color data that we have. But for me, the cool thing is the color data do not match the expectations of this Kuiper belt capture model. You know, you give it a chance, could have worked out, didn't work out.
Thank you. Yes. So for Bonnie, about looking at Triton in the framework of the comparative planetology of the N2-dominated atmosphere, so we have Pluto. Do you expect that the same kind of process that you see of brightening could happen on Pluto, or in other ways, can Triton be used as a sort of quicker proxy to determine the seasonal variations of Pluto?
Yeah, well, it looks like a similar process is happening on Pluto. And when we got there, when New Horizons spacecraft got there, we thought we'd see, something change, polar cap that was sublimating away. But the main thing that's happening there is active geology that kind of swamps the whole thing. I mean, there were changes on Pluto that were observed by the Hubble Space Telescope, Mark Buoy's work, as well as changes in the light curve that suggested a similar thing as on Triton. But I think we've kind of forgotten about that because we're trying to figure out what's going on in the heart of Pluto. But as you say, Triton really is a proxy because we expect seasonal volatile transport to occur. And there are a couple things you need. First of all, you need a high obliquity. You have to have that tilt because that's what causes the seasons. You have to have an atmosphere, at least a thin atmosphere, which means it has to be a fairly large body because, it has to hold the atmosphere. So it looks like there are other Kuiper belt objects that could undergo seasonal transport, such as Eris is one that, and it's very bright, and yeah, I mean, this is one of perhaps, not many, because you do have to have a large object, you have to have an atmosphere, but maybe a dozen such objects that exhibit this kind of seasonal transport of volatiles.
Thank you. So the last question for Ted. There is a lot of discussion these days about the comet asteroid continuum, and Phaethon is quite nicely positioned. So do you think that your results support the idea that it's a kind of intermediate object, or it's more on one category or the other?
I think it's definitely somewhere in the middle. And I think a lot of people have suggested that for a long time. I know Dave has mentioned that in papers. I think part of the issue is, even if it is somewhere in the middle, you still want to have an idea of, where did this object come from? What other objects is it related to? What can we say we understand about its properties? And with Pallas, it was kind of a nice pairing because Pallas is this large object. It looks similar, and they both. Pallas is known to have lots of volatiles. People have detected hints of water on its surface, but Phaethon is dry as a bone, partially because it goes through oven-like temperatures. I kind of think that part of the problem is that Phaethon has been so cooked that answering a question like, is it cometary, is it asteroidal, where does it fit on that continuum? And it's definitely somewhere in the middle. I wonder whether or not that information's still around or whether or not it got scorched. I think I would generally probably guess that it's probably somewhere closer to asteroidal, but that feels like a non-committal answer. But I don't know.
Polarization measurements, I think, show that they're similar. Now there's Ben with also some cometary properties.
Yeah, the polarization says it looks very similar to Pallas, which is very interesting.
Yes.
Yeah.
Thank you very much.
Hanako Widering with Space.com. I have a couple questions for Ted. The first one is regarding the blue color. What can we learn about the composition of Phaethon? Because of its blue color, it's kind of weird. And are there any other, I guess, similarly colored things that are also pretty weird that you would want to study that kind of resemble Phaethon? And then also, in regards to the Geminid meteor shower, so with meteor showers, I I kind of understand with comets how they leave what I call comet crumbs behind, and then that trail is what we go through, and it creates the meteor shower. But by what mechanism does the asteroid, I guess, leave this trail of crumbs that turns into a meteor shower?
Okay, so I'm going to try to answer all your questions. You might need to remind me as I get to the
Okay.
end. So in terms of blue things, there are other blue asteroids. There's just not a lot. Probably the most famous one, NASA's already decided to spend $1 billion to get to. It's the target of the OSIRIS-REx mission, Bennu. Actually, this is part of the reason that we started working on this originally is that Phaethon and Bennu are similar spectroscopically, so they both have this sort of unique, strange blue color. The ideas of how you actually get an object to have a spectrum like these, it's a little bit challenging, but people generally think it probably has something to do with this intense heating. Is that, at some point in the past, it could have been, more like a sort of normal volatile rich asteroid out in the main belt, red in color, normal looking. But in the lab, when you heat up certain meteorites to, something like 1,000 degrees Kelvin, coincidentally close to what Phaethon is like, they actually start to turn blue. But only certain kinds, and it seems to not always work perfectly, and it's not a perfect match for Phaethon, but that's the idea. So then the next question was about how the Geminids were made, right?
Right.
Yeah. So again, people don't know. The debate is basically, if it's a rock, it's just some rocky asteroid, maybe the Geminids are made in that, Phaethon at some point in the past, maybe it had an impact, it was shorn apart for some reason, and we're essentially just seeing the debris from this catastrophic breakup. So in that case, you're seeing all these, dusts and essentially like blood splatter, to be gruesome, from this really violent event. Alternatively, if it was cometary at some point in the past, maybe it, made the meteor shower in the normal way, left behind those comet crumbs, like you said. But then since then, it's been cooked through and turned off, and it just looks like a rock.
Thank you.
And it's about 1 in 20 asteroids are blue, 1 in 20. So they're not extremely rare, but they're fairly rare.
All right, I have a question here for Bonnie from Rick Lovett at Cosmos. Looking at the big picture, what does watching this process on Triton teach us about planetary processes in general? And more specifically, if this were to happen on Eris as well, what would that tell us?
Well, I think it is kind of moving the whole idea of seasons and volatile transport from Mars and the Earth, which is where we've really seen this, to the outer solar system, that it's a similar type of process. It also tells us about the evolution of the atmosphere on these objects. And also, one thing that I didn't mention, because it may not apply to Triton, is it's really hard to deconvolve these processes from active geology. I mean, that's the thing that really blew us away on Pluto. We did observe frost changes. We thought it was going to be a polar cap migrating, but it was just the heart of Pluto that has glaciers of all things. First glaciers, active glaciers discovered outside the Earth. So with the Eris, it's a similar sort of thing. It should have volatile transport if all the models are correct, but it's so high in reflectivity. It's as bright as Enceladus, which is an active moon of Saturn, that maybe it is just the whole volatile transport process is being overcome by some geologic process. So in general, it does tell us about planetology, about seasonal processes and these outer objects in the solar system. But I think these more spectacular results of active geology maybe make it all secondary and wipe out all the stuff we're doing studying pinpoints of light. Because you need a spacecraft, you pretty much need a spacecraft mission to see the activity like we saw on Pluto. You just can't observe that from the ground.
Thanks.
Yeah.
And we have a question for David from Chris Crockett from Sky and Telescope. It seems like there were some similarities to Centaurs. Is it possible that Centaurs and Trojans have a common parent family?
So the Centaurs actually are one of the populations that I'm pretty sure are scattered out of the Kuiper Belt. So the color distribution of the Centaurs is very broad, and the Centaurs include this very red material that we see in the true Kuiper Belt objects themselves. So that's a difference between the Centaurs and the Trojans, because the Trojans basically are depleted in this ultra-red stuff. There has been a paper in which it was suggested that most Centaurs come from the Trojans of Neptune. And I think that's not the case, right? Because the color distributions are not the same. What we also see in the Centaurs is as they migrate in, many of them become active. They start to eject dust, probably as a result of sublimation of ices or crystallization, at about the orbit of Saturn, which is at 10 AU. And inside that, they are themselves depleted in ultra-red stuff. So you get the idea that there is a thermal modification process that occurs when you bring objects in from the Kuiper belt to Jupiter distances, but it doesn't help you with Neptune, because Neptune is way out, it's way out at 30. So the Centaurs are not color-wise like the Trojans, but they do show evidence of activity at 10 AU, which is one of the processes that might occur on the Jupiter Trojans, but not the Neptune ones. Conundrum. Yeah.
Rick?
Okay, I'm Rick Feinberg from American Astronomical Society press officer. I have a question for Teddy. So normally space weathering makes asteroids redder, I understand. But in the case of Phaethon, you're talking about how it's getting cooked. So you talked about how the cooking can turn asteroids blue. I'm wondering if you know whether cooking also can change albedo, because you mentioned the albedo difference between Pallas and this object, and I'm wondering if that could also have arisen from the heating.
Yeah, so I didn't want to get super into the weeds in this in the talk, but I'm glad you asked. Basically, when people cook these meteorites in the lab, and they measure their albedo and their spectral response as they get heated, the argument we were trying to make is basically, often there are accompanying albedo changes. So, if we were looking at Pallas and Phaethon, for instance, we saw that they had subtly different albedos and subtly different spectra, that wouldn't be that surprising, actually. You could imagine a scenario where both change in tandem. The problem is that it's really hard to change one. So Phaethon and Pallas have very, very similar reflectance spectra, throughout the entire range we looked at. And this has been noted for more than probably about a decade now. But there's no way to basically not change the spectra if you're going to change the albedo by having it, in our case. Regarding the question of space weathering, things do generally turn red. That's definitely true. But I think the key to understanding in the case of Phaethon is I think in Phaethon's case it's happening much quicker and more intensely. Space weathering can take a long time. It's not a universal thing, but with Phaethon, every time it goes through the surface, it's even losing dust. Dust actually, rocks shatter on the surface and get swept away. So even if there was anything getting space weathered, chances are it's getting cooked and then tossed out anyway. So.
And that goes back to Irina's question about the origin of the Geminids, right? You're saying stuff does get blasted off when it's at perihelion?
Yeah, I mean, at this point, I'm wandering into papers that Dave Jewitt has written, but in this case, the amount of dust that gets swept off is nowhere near enough to sustain the Geminids, so it can't be that. It still has to be something else.
So I have a silly question for David. Why Jupiter and Neptune and not Saturn and Uranus?
Basically, the other Trojans are destabilized by, like Saturn's Trojans destabilized by Jupiter, so massive next door. And the Uranus Trojans are destabilized by some resonance with another planet.
And not Neptune.
Huh?
Not Neptune.
Neptune is the outermost giant planet, right? So it's on one side it's safe, and the other side is just Uranus, so it's okay. But Uranus has got a Neptune over there and Saturn over there. Yeah, so dynamically that seems to be the case. There could be temporary captures. Stuff coming in is sometimes hung up on a resonance, but we don't care about that. We know what that is. Yeah.
Just a brief clarifying question from Rick Lovett at Cosmos for Bonnie. The ice we're seeing on Triton is nitrogen ice?
Oh, yeah, it's nitrogen and probably some methane, too. Yeah, I forgot to say that. It's definitely not water. It's like a rock. Yeah, methane and nitrogen.
Great, thanks.
All right, so if we have no other questions, we'll end the press conference here. A reminder that Teddy Kareta's press release went out today, so watch out for that. And we'll be back here tomorrow at 12:15, and we'll have the New Horizons press conference tomorrow. And on Thursday, we have the Hayabusa 2 press conference, so hope to see you tomorrow. Thank you.